Earth is called blue planet, and rightly so, just because of one substance that exists everywhere, on the surface, in the ocean and in atmosphere, and it's water. Let's examine how extraordinary physical properties of water result into its unique chemistry, and also explore the tremendous impact it has on all living systems. Water molecule is relatively small in size, just 1 nanometer, a millionth of a millimeter, consisting of 1 atom of oxygen and 2 atoms of hydrogen. This gives the molecule, and therefore water itself, the familiar chemical formula of H2O. The formula is familiar, but what does it mean? In these models, the red ball represents oxygen and the white ball represents hydrogen. Observe the molecule. It's not linear. It has a bent geometry with HOH bond angle of 104.5 degrees. Due to the presence of a free electron pair, the hydrogen-oxygen-hydrogen angle gets reduced to 104.5 degrees. OH is a covalent bond. Oxygen has a higher electronegativity and pulls the shared electron pair closer to itself. As a result, the hydrogen end of the molecule acquires a partial positive charge and the oxygen end a slightly negative charge. There are many situations in which this property of water manifests itself. Let's take this charged rod and hold it close to the stream of water. The stream gets deflected, establishing the presence of charged particles, the polar water molecules. If we try the same experiment with a stream of hexane, there is no deflection. Hexane is a non-polar liquid. For most substances, it's true to say that solid form is more denser than the liquid form. A significant exception to this rule is water. Ice sinks in alcohol, but floats in water rather than sink in it. It means ice is less dense than water. Due to its polar nature, the positive hydrogen end of one molecule attracts the negative oxygen end of another molecule and forms bonds. Such bonds, known as hydrogen bonds, are continuously made and broken, lasting for as little as 10 picoseconds. The bonds are relatively weak. Due to large number of bonds that can form, their influence is continuously felt. In fact, if there were no hydrogen bonds, water would boil off at hydrogen bonding is also responsible for water's role as one of the best solvents. Water is said to be closest to being the universal solvent. Ionic substances such as salts dissolve in water because polar molecules surround the component sodium and chloride ions. If water molecules come between ions at the edge of a crystal, it weakens the attraction between them. The layer of water surrounding the ions insulate them from one another and prevents them from joining together into a crystal again. This is also the reason why substances react in solution more readily than in solid form. Copper sulfate powder and sodium hydroxide pellets do not react together when dry. Now we dissolve each in water. Let's see what happens when we mix these two. A cloudy suspension of copper hydroxide is readily formed. Compared to most other substances, water heats up quite slowly. A lot of energy has to be put into liquid before its temperature rises. And it cools down also very slowly when the heat source is withdrawn. This is a very interesting consequence of hydrogen bonding. Specific heat measures the extent to which a substance resists change in its temperature when it absorbs or loses heat. Water has high specific heat, 4.186 joules per gram degree Celsius, which is twice that of ethanol and 4 times that of chloroform, and more than 10 times that of copper. This means that energy needed to boil a kilogram of water could heat 1 kilogram of copper to more than 800 degrees Celsius. That is why it takes so long for this hot water bag to cool down, or coffee stays hot longer than thick soup. For the same reason, water is used as coolant. All organisms have high water content in their body. One of the consequences of this high water content is that organisms are able to maintain constant temperature of their body despite high fluctuations in ambient temperature. On a larger scale, the water in lakes and oceans absorbs and stores large quantities of solar energy and maintains constancy through the seasons of the year. This was specific heat of water in action. Now let's look at some other properties of water. Of all substances commonly found on earth, water is the only substance that exists in all 3 states of matter under normal conditions. This water cell is filled with pure water and sealed so that no air is present. It then contains liquid water and water vapors. The cell is cooled using liquid nitrogen. A layer of ice is formed. Here we have a situation of ice, water and water vapor coexisting at the same temperature. In fact, at the surface of this ice, you have ice melting into water and water evaporating into water vapor continuously. You also have water vapor condensing to water and water condensing to ice. At a given temperature, if the system is closed, there is an equilibrium established between the 3 phases. At low pressures, water boils off at lower temperatures. On mountains like this, water boils at about 90 degrees Celsius. And in a pressure cooker, water boils at a temperature higher than 100 degrees Celsius. Since the pressure due to vapors inside it can rise much above the atmospheric pressure. Ice at 0 degrees Celsius takes in a surprisingly large amount of heat, 80 calories per gram, to become water at 0 degrees Celsius. This heat was given the name latent heat of fusion by Joseph Black. And that's exactly why ice cubes are preferred to cool a soft drink. And also why snow on mountain tops lingers so long, even after the air temperature has risen well above the freezing point. Similarly, water at 100 degrees Celsius absorbs 540 calories per gram to convert to steam at 100 degrees. We call this heat the latent heat of vaporization. This explains why steam is hotter than boiling water and machines like this work. This explains why many living beings dispose excess heat by evaporative cooling and why sweating profusely helps keep the body cool. In general, evaporation has a cooling effect on the environment, whether a leaf, a forest, or an entire land mass. Interestingly, water has a high freezing and a high boiling point. Most substances with a comparable molecular mass exists in gaseous state at the temperature at which water exists in liquid state. For example, water with a molecular mass of 18 has a boiling point of 100 degrees Celsius. Compare it with ammonia with a molecular mass of 17, very close to water, has boiling point of minus 33 degrees Celsius. Again, methane with a molecular mass of 16 has boiling point at minus 164 degrees Celsius. We have already discussed a property of water known as anomalous expansion of water. Water is denser than ice. As a consequence, ice floats on water. During winters, water in the stream and lakes begins cooling. They become denser and sink, being replaced by warmer water from below. Gradually, the top layers freeze, leaving the bottom layers as liquid water at 4 degrees. This allows fish, plants, and other organisms to survive through harsh winters. While the lakes and ponds freeze, oceans do not, except probably near the poles. The reason for this is its salinity. The presence of salt lowers the freezing point from 0 degrees to minus 18 degrees. A molecule deep within a container of liquid is attracted by all of its neighbors. It is pulled in all directions at once. It is like a tug of war in which no one wins. It experiences no net force. But think of a molecule at the surface of the liquid. It has no neighbors above it, and so experiences a net downward force. The downward pull on all the surface molecules creates a kind of tension over the surface of the liquid, which acts like a rubber skin of a balloon. Just as molecules of liquid attract each other, they can also get attracted by other substances. The force of attraction between two unlike molecules is called addition, and this is why things get wet when they are dipped in water, and this is why waxy substances do not become wet. It is this surface tension that gives water droplets their spherical shape. And it is this surface tension of water that permits a container to be filled slightly above its surface without overflowing. Watch this insect walking on the water. The film of the water surface is not broken. A small dimple is formed. Again, it is the surface tension that makes it possible. Water molecules are attracted to glass more strongly than they cohere. Water is therefore pulled up the sides of a glass container, giving a concave meniscus. Conversely, mercury atoms cohere more to each other than they adhere to glass. Mercury therefore has a convex meniscus, which minimizes contact with the glass. Observe this water rising in the tube. We call this capillary action. The addition of water to the substance with surface electrical charges is responsible for capillary action. The narrower the tube, more the adhesion force that defies gravity, and higher the water rises. Mercury shows no capillary action. Capillary action is what makes water spread on paper or creep between the fibers of a kitchen towel. Without this, you could not mop up spills. This is also the reason why the ink rises in this piece of chalk. It is this force of surface tension and capillary action which makes water go up from the roots, moving distances of several meters to reach up to the leaves. The polar nature of water makes it extremely powerful and useful solvent, and this permits a whole host of chemical and, more importantly, biochemical reactions such as respiration and photosynthesis. We have explored some fascinating properties of water. It is these properties that make water vital to all life processes. Unlike most other substances which become increasingly dense as the temperature falls, water first becomes dense and then begins to expand again below 4 degrees. The high specific heat and the high heat capacity enables it to act as an effective buffer against extreme temperature fluctuations in the environment. Water is very vital as it is an excellent physiological medium and all-purpose solvent. Life has evolved from and has got linked to water. We have also found very many ways of harnessing it for a variety of purposes. Let's end this story with a big salute to this molecule called water. Water, water everywhere should not make us forget, even for a moment, its exceptional, extraordinary, and unique contribution to our very existence on this beautiful, unique blue planet.